Welcome to Frank Stajano Explains and to the Algorithms course at the University of Cambridge. This video is one of several in which we tackle problems using dynamic programming. And the problem we tackle in this video is to find the optimal sequence in which to perform a chain of matrix multiplications. This is after understanding that although the result stays the same, the order in which we multiply the matrices dramatically affects the number of elementary operations we need to perform.
Another problem with our dynamic programming technique, and this problem is multiplying matrices together. Multiplying matrices is an operation that, as you know, is associative. So if I have to multiply A times B times C, and A is a 4 by 3 matrix, and B is a 3 by 2 matrix, and C is a 2 by 1 matrix. First of all, I have to check, are they compatible? Yes, well, the middle dimension has to be the same, otherwise the matrix multiplication doesn't work, because I have to take a row vector from here, column vector from here, and blah, blah, blah. But it works. It works for everything. So I can do AB times C, or BC first, and then A times BC. And I'm going to get the same result. So does it matter what I do? Numerically, no, because I will get the same number. But computationally, yes, because to get to that same final matrix, I will do a number of operations that is greatly dependent on the order in which I decide to multiply my matrices. So for example, if I do the regular thing, and I just go from left to right, and I multiply A and B, how many operations will I do? Well, let's just consider that multiplications are so much more expensive than additions that I will only count how many multiplications I do. So how many multiplications I do when I multiply these two matrices? Well, these two matrices will result in a matrix of size 4 by 2, and in every one of those cells, I have to multiply, I have to have a row vector here and a column vector from here, for every entry of which I will have to do a multiplication, then add them all together and stick them in here. So I do as many multiplications as there are items in this common dimension. So I basically do 4 elements, 2 elements, and 3 multiplications per element. So I end up multiplying these 3 numbers. And so 4 times 3 is 12, times 2 is 24. That's AB gives me 24 multiplications. If I then multiply by C, then I have a matrix that's 4 by 2. 4 by 2 by 1, I have to multiply 4 times 2 times 1, which gives me 8. 8 more for multiplying those two. So 24 multiplications for this, plus 8 multiplications for the top level 1, which gives me 32 multiplications, total cost of AB times C. I might, however, also first multiply B times C. So B times C gives me 3 times 2 times 1, which is 6. And then I get a 3 times 1 matrix. And if I multiply this by the 4 by 3 matrix I have here, 4 by 3, 3 by 1, then 4 times 3 times 1 gives 12. So the total is 12 plus 6 makes 18 to get my 4 by 1 matrix, which is the same matrix as the one I got before, but before I paid 32 multiplications to obtain it, and now I only pay 18, which is almost half. So it pays to just be careful initially about which order I do the multiplications in. Now, can I try looking for all the possible ways? Well, there are a variety of ways. You can do this, you can do this, then you can do this, then you can do this. Okay. You could also do this, and this, and this, and this. What else could you do? You could do this, and this, and this, and this. You can flip them around. You can do a variety of other things. And with 5, there's already quite a few more than the 2 that we had in the case of 3. Can you figure out a systematic way of trying all of them? Well, the systematic way would be to say that whatever this total product is, when I write out what I did, this was A, B, C, D, E. There's going to be a top-level multiplication somewhere. In this case, it's here, this one. The top-level multiplication here was this bracket times E. Top-level multiplication here was AB times this other bracket. So the top-level multiplication can occur here, or here, or here, or here. Then what I'm left with is finding the best way of doing the product of a shorter sequence of matrices that are adjacent. So it's basically the same problem with a smaller n. So again, you have the optimal solution for size n is made of the combination of optimal solutions to smaller problems. And you can write yourself a small program to compute how many varieties there are, how many cases there would be to check if you wanted to cost them. For each one of them, for each one of the basic matrix multiplication, you can say how many multiplications, elementary multiplication it involves by multiplying the 3 dimensions, the common one and the 2 non-common ones. And you could cost all of them. However, similarly to what we've seen in previous cases, the number of cases that exist grows very quickly with the number of matrices. If you write yourself the program I recommend you do, it's very easy, you will see this number growing very quickly. Again, it's an exponential growth, more than polynomial. So we don't really want to have the approach of looking for all possible alternatives and costing each of them and then finding the one that costs the least. We want something a little bit smarter. And the first thing we need to do is to cast the problem in the form that we have used for the rod cutting. So I'm going to say, if this is a sequence of matrices, and this one, A1 has dimensions P0 times P1, A2 has P1 times P2, and you see that this time I'm numbering them from 1 because I also need one less to do the previous index. So it's like having 0, 1, 2, 3, 4, 5, 6 in between the matrices in here. So in fact, it is the case that 0 is still over here. So I'm going to use this notation of Mij to mean the minimum cost of multiplying Ai times blah, blah, blah times Ij. So M25 is going to be the minimum cost of multiplying A2, A3, A4, A5, which I could do in several possible ways. Whichever way costs the least is going to be denoted by Mij. So what is going to be the cost of Mij? This is going to be equal if, well, I is going to be less than or equal to j, but if I is equal to j, it means the cost of multiplying M33 is going to be the cost of A, 3, and 3. If I equals j, then it's going to be 0. I don't pay anything. If I is strictly less than j, then the cost of doing that is going to be a cost that depends on where I do my top-level multiplication. So top level multiplication is going to be somewhere between I and j. And so this is something that you do have in your handout. I'm going to have the minimum cost for every possible position where I could do the cut. Okay, in an interval which includes I and does not include j, of the minimum of doing the top level multiplication and doing the minimum of the two parts that I'm going to do them as smaller cases. So the top level is going to be, what are the dimensions of this? It's a matrix that has, if this is matrix 3, then this index is 3 minus 1, and then to 5, then this is 5. So it's going to be I minus 1 times the place where I do the split, which is k, times the last one, which is j. So I'm writing pi minus 1 times pk times pj. These are the three dimensions of the top level matrix in the cut. And then the two sides, which are minimum cost of cutting from I to k and minimum cost of cutting from k to j. So this is where we'll pick up next time by doing the same work as we did for the rod cutting with this equation. Last time I finished halfway through working through the matrix multiplication thing. And what I was doing last time was writing out this part of the formula. I also made a mistake. So in preparing for what I was going to say this morning, I said, let me just do a numerical example, so maybe I will not make the same mistake. The minimum cost of multiplying matrices from 2 to 5, so the minimum cost of computing A2, 3, 4, 5, is going to be the minimum over putting the cut here, here, or here, of doing the top level multiplication, and the minimum of doing the left part and the right part. So it's going to be the minimum for the cut point being here, position 2, 3, or 4. So this is the k. It goes over here, not to 5, because I would place it here. This is the left side, and in this case it would be M22, which has no cost, and the right side, which is M35, and this is where I made a mistake last time. I didn't have this plus 1 here, so 2, and the next one starts from 3. And then the cost of doing this top level, this times this, which has dimensions this times the common one here times that. So that's P1 here, P5 here, and the pk in the middle is this one. And then if I generalize this 2, 5 to I and j, I get this one. All right, so that's where we left off last time. And what I wanted to do now was to say, all right, let's see how we can compute this instead of top-down. This is starting from A16, breaking it up into the various costs. Well, I don't know where it's going to be, but somewhere in there's an optimal solution. Let me find the minimum of all these possible things. But I don't know any of these, so I have to go down into doing it for smaller and smaller systems, all of which have their own optimal solution, and the combination of them gives me the top level one. So the dynamic programming approach lets you instead work bottom up. If you work bottom up, then you are able to not ask things that you haven't done yet, but only consult things that you've already computed previously. So if I make myself a matrix, and it is a square matrix indexed by I and j, but because I only has to be, it is only allowed for I to be less than or equal to j, then it's a diagonal, the top triangle of a matrix, and so I tilt it sideways, and I write it like this so I can put it on top of these matrices to say the part of the square I'm not drawing is the one where j would be smaller than I, and so I'm not interested in those because it can never happen. And in here what I put is at any cell, for example this cell, I'm going to put the minimum cost from A2 to A6. And the minimum cost from A2 to A6, this formula tells us, is the minimum over choosing to cut here, 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 or here, of the minimum cost of the left side, the minimum cost of the right side, and the cost of combining them together. But if I compute this from the bottom going upwards, then any matrix by itself has cost 0 because I'm not doing any multiplications. And anything on this first line, which I've already filled in at home, is simply, there's no minimum to be done, it's just the cost of multiplying these two matrices. So in this case, 30 by 35 by 15 makes this number, and I get a 30 by 15 matrix. 35 times 15 times 5 gives this number, and I get a 35 by 5 matrix, and so on. So if I wanted to fill in any other entry in this matrix above here, if I keep going in rows from the bottom up, every time I need a value from this formula, the value is already in cells that I computed in previous layers. For example, if I wanted to write the appropriate thing in this cell here, then I would have to say this is 4, 6, excuse me. So for 4, 6, it means I could put the cut here, or I could put the cut here. If I put the cut here, I'm doing 4 times 5, 6. If I put it here, I'm doing 6 preceded by A4, 5. So I have to check both of these, but this one gives me this cost. This one gives me this cost. So I have to do the minimum between taking this one times this, and taking this one times this is a matrix 5 by 10 by 25. 5 times 10 times 25 is 125, 1250, right? Plus, so if I magnify this, this would be 5, 10, plus the 500 for this one. So that gives me 6250. That's the cost for doing A4 times the other one. Instead, if I do A4, A5 times A6, then A4, A5 is, as I can see here, is a 5 by 20 matrix, which I'm going to multiply by this 20 by 25 matrix, so I have to pay 5 times 20 times 25. 5 times 20 is 100, so 2,500. So I'm paying 2,500 plus the cost of doing the other one, which was here, 1,000, and that's the cost of doing A4, A5 times A6. So that gives me 3,500. So at this point I do the minimum. Which is the minimum between this one and this one? It's this one. And so that's what I write in here, 3,500. And either way, I get the matrix that is 5 times 25. And that's how I fill in each one of these other cells, always computing based on things that I had before, and then I can move on to another layer, always computing on things I had before. And eventually I will get here, which gives me the optimal solution for the whole multiplication from A1 to A6. And at that point, the minimum is going to be not just between 2 options, but between 1, 2, 3, 4, 5 options. And I will get the total number of multiplications. Another way that I could do the same is by working top-down, and as I recurse, I memoize instead. And if I memoize, I will save on redoing the same problems again and again. So if we wanted to summarize the general principles of dynamic programming from the examples that we have seen today, that we have seen so far, then a typical thing is that there exist many choices. This is coming straight from your handout. There exist many choices. Each choice has some kind of score which must be minimized or maximized. It's an optimization problem. And in the example we just finished, each parenthesization of the matrix expression is one possible choice, and the score is how many multiplications I do, and I want to minimize the number of multiplications. Typically, these many choices exist. There's exponentially many of them in the size of the problem, and so it is not feasible to compute the score for each and then see which one is smallest. And here, the number of choices is the number of possible ways to put the parentheses around the matrices. Another important feature and necessary for using dynamic programming is that the optimal solution is made of optimal solutions to smaller problems. That's what allows me to write that type of recurrence of mij in terms of mij's for narrower ranges. The argument that is always used when solving a dynamic programming, solving a problem with dynamic programming, is that I argue that once I've split it into smaller things, the smaller things, I must take the optimal solution for them, because if I didn't take the optimal solution, it would be possible to substitute whatever I take with the actual optimal solution and get a smaller value, which meant that what I was taking was not as good as it could have been. And this is the reason why dynamic programming is useful, because the sub-problems I'm solving have overlap. In the case where the sub-problems don't have overlap, it's the thing, the divide and conquer thing that we've used for merge sort, for example. I just solve the sub-problems independently, and that's fine. But here, if I did solve the sub-problems independently, I'd be solving the same ones too many times. So all these things will recur in different guises in all the problems that are suitable for solution with dynamic programming.
Thank you very much for watching, especially those of you who clicked the like button and subscribed to this channel. This means a lot to me, and it also encourages YouTube to show this material to other people who might benefit from it.